Hello everyone, this is Dr. Zach. For Unit 3, Lesson 3, we're going to discuss integration and how it relates to moments, mass, and centroids. So for your lesson preview, here is what I'd like you to recall. Force is equal to mass times acceleration. Recall that mass is not a weight. A weight is a type of force and it is dependent on gravity. Knowing that, I would like you to find the mass in slugs of a student who weighs 125 pounds. Go ahead and work that one out. The main objective of this lesson is to find a point P on a thin plate of any given shape that's going to be able to, so that we can balance this shape in a horizontal fashion. Now this point is called the center of mass for the plate. So if we put a fulcrum at point P, we're going to keep that plate flat. Let's begin looking at a line. So our goal is to keep this line from tipping either downward on the right or downward on the left. We have masses scattered about the line, and each one of these masses is a particular distance from the center, which we're going to call 0. So a moment at a point is going to be equal to the mass multiplied by the distance between the mass and another point, which will be our origin. M sub O is going to be the sum of the moments, or the moment of the system, about the origin. So if we can keep M sub O equal to 0, then the system is said to be in equilibrium. If our system is in equilibrium, then it will not tilt to the right and it will not tilt to the left. That horizontal line will stay nice and flat. If M sub O is not in equilibrium, then the center of mass is defined to be some other point, x bar, at which the fulcrum could be relocated to obtain this equilibrium. If your system were translated those x units, then each coordinate of x sub I would become x sub I minus x bar, and we would be able to write the sum of each of these masses multiplied by their distance is going to be equal to 0. Let's solve this equation for x bar so that we know where our fulcrum should be placed. So if we distribute m sub I through the equation, we now have the sum of I equals 1 to n of m sub I times x sub I minus the sum I equals 1 to n m sub I multiplied by x bar, and that of course must be equal to 0. Now what we're trying to do is solve for x bar. Fortunately, x bar is not going to be part of the index of summation and can be factored out of the sum. So that leaves us with the sum I equals 1 to n m sub I x sub I minus your x bar, and then that will be multiplied by the sum I equals 1 to n m sub I, and of course that still equals 0. One more time, we are trying to solve for x bar. So if we take the expression and move it to the right, we're going to be able to factor. What we will know once we solve that is that x bar is going to be equal to the sum I equals 1 to n, the m sub I, x sub I divided by your sum I equals 1 to n of m sub I. All right, now let's examine what we have here. So the fulcrum should be placed wherever you have the sum of the masses multiplied by their distances to your origin divided by the sum of all of your masses. So if we can do that little tiny bit of math, we're going to be able to figure out exactly where to place the fulcrum so that our line does not tilt. So let's review. We're going to let the point masses of M1, M2, all the way to Mn be located at the values x1, x2 through xn. The moment about the origin, m sub O, is going to be the sum of each one of their masses multiplied by their distance, and the center of mass, which is called x bar, is going to be the moments about the origin divided by the sum of all the masses. For our first example, we're given all the masses of each of the objects placed on a line and where they are located. We're asked to find the moment of the system about the origin and the center of mass. So as you recall, the moment of the system about the origin is going to be equal to the mass multiplied by its distance, in this case -2, so it's left of the origin, plus 20 multiplied by 3, which means it's 3 steps to the right of the origin, plus the mass, which is 10 multiplied by 7, and we figure out that sum is going to be equal to 80. Now the center of mass, or x bar, is going to be equal to your moments divided by the total mass, so m for total mass. So we'll have 80 divided by, now add up all of your masses, and you should come up with the 55 reduced, and what we know is that the moment over m is going to be equal to 16 over 11. Now if we think about that, that's going to be at 1.45. So in order to keep your system in equilibrium, we want to put the fulcrum 1.45 units away from the center. All right, now let's think about what happens in 2 dimensions. We're going to treat the x values and y values separately. Now, the moments about the y are going to measure the tendency of the system to rotate about your y-axis. And the moments about the x are your tendencies to rotate about your x-axis. So let's explore that just a little bit further. If I draw the distances from the y-axis, so the moments about y, notice all of these distances are actually x values. And if I were to draw the distances to the x-axis, you got it, these distances are actually y values. Now, I find that to be very interesting. The center of mass can be found by x bar and y bar. So when we consider what's going on here, the moment about your y-axis are going to be each of the individual masses multiplied by their distance in terms of x, whereas the moment about the x-axis is going to be the mass multiplied by their distance with respect to y. The center of mass, so this is to help you keep your plate balanced that we were talking about earlier. Your center of mass is going to be from x bar is going to be your moments of y divided by m, and for your y bar, it's the moments of x divided by m again, where m is the total mass of your system. So in order to keep this equilibrium in a 2-dimensional system, we need to talk about how it's rotating in both the x and the y direction. So for example 2, we're to find the moments and center of mass for the system of objects that have the given masses found at those given points. Let's start this problem by first finding our total mass m. So the total mass for this problem is going to be your 3 plus 4 plus 8, or 15. The moments about your y-axis are going to use your x values, and those values are going to be the mass multiplied by your -1 plus your mass, which is 4, multiplied by 2, and the mass, which is 8, multiplied by 3, which is 29. So x bar is going to be equal to the moments about the y-axis divided by m, or 29 over 15. Now, the y bar is going to come from the moments about your x-axis, and in that case, we're going to have, once again, mass 3 times 1 plus mass 4 times -1 plus mass 8 times 2, which will add up to give us 15. So y bar, which is equal to your moments about the x-axis divided by your total mass, is going to be 15 over 15, which is 1. So when you consider this system, in order to find equilibrium, we want the center of mass to be x bar, comma y bar, And the center of mass in this two-dimensional system will be 29 over 15 for your x value and 1 for your y value. So we'd want to set the fulcrum at that point on this system. Now that we've had examples in the 1D and 2D systems, let's talk specifically about the flat plate, which is called a lamina. Now this lamina that we're going to draw has uniform density, and it can take any shape that we want, but as you can see, it might have a little bit more weight on one side than it does on the other side. What we're trying to do is find the center of mass of this plate so we know where to place the fulcrums to keep it horizontal. So the center of mass of such a plate is called the centroid of region R. All right, so to determine the centroid, now there are several principles that we can use. If we have some symmetries on our plate, then we can figure out the x and y values very nicely. So in this case, we have symmetries about the y-axis, in which case we know that the centroid is also going to have to lie somewhere on the y-axis in order to keep this balanced. So if we have symmetries, this makes the problem a whole lot easier. Otherwise, we're going to have to find the x values and the y values in order to define where that centroid would be. Now let's think for a moment about a rectangle. The rectangle has two lines of symmetry. So if it has two lines of symmetry, one that is horizontal and one that is vertical, it is really rather easy to find where the centroid would exist. It would be where the vertical and your horizontal line intersect. Now, according to this little graphic, they're going to intersect at the values of x, comma, y. So the centroid for this little rectangle should be x, y. And we will say that the x value is going to be some sort of c sub k, in which case the area of this rectangle is going to be equal to the height, which is f c sub k, multiplied by c sub k. Well, the area could be very important because what we know is that mass is equal to the density multiplied by the area. So if we consider this one rectangle to be one little slice of a rectangle in our lamina, what we're going to be able to do is figure out the moments of this rectangle about the y-axis and about the x-axis. Now, as we consider what's happening about the y-axis, your moment is going to be your mass, which is rho f of ck times your delta x multiplied by the distance to the y-axis, which we know is c sub k. So the moments with respect to y will be equal to the sum of all of those rectangles. And then if we find the moments with respect to x, let's think about what's happening to the x-axis. Well, from the x-axis, what we know is that those moments are once again going to be equal to the mass multiplied by 1/2 of the height of each one of these rectangles. So what's happening to our arbitrary lamina? If we take an infinite number of those rectangles, the moments about the y-axis are going to be rho times the integral from a to b x f of x dx. And the moments about your x-axis are going to be equal to rho times the integral 1/2 of f of x quantity squared dx. So the center of mass, or our centroid of our plate, is defined to be mx bar, which equals my, and my bar, which equals mx. However, the mass of the plate is density times area. So if we have mass of the plate is density times area, we could then know that we can solve this for x bar and for y bar. So x bar is going to be my over m, and y bar is going to be the moments about x divided by m as well. And m is equal to rho times the integral from a to b of f of x dx. So now what we know is that we can take the moments about y divided by m, moments about x divided by m, and we will know x bar and y bar. So our centroid can be found by solving for x bar and y bar. Notice that the density of your lamina will cancel out for each of these and can be ignored. For example 3, we're going to find the center of mass for our semicircular plate of radius 4. So of course we want to draw a picture. Here's our semicircle, radius 4. Make certain that you put in some values so that you have a good idea of where our points will be. So once we draw this, we know that x squared plus our y squared has to be equal to 16, and we can solve for both x and y depending on what we're looking for. First, we'd like to find x bar. So x bar is going to be equal to the integral for the moments about the y, which will be x times f of x dx, going from -4 to 4, and that will be divided by the mass, which is your area, and the area of a semicircle is 1/2 pi r squared, so we will have times 16 in here. Now, y bar is going to be equal to the integral from -4 to 4. In this case, we're going to have f of x dx. That's f of x is going to be squared, and we will divide it again by 8 pi. Now, let's look more closely. If we let f of x be y equals the square root of 16 minus x squared, we can now substitute those values in for our f of x equations. But we are going to be able to be a little bit more clever than that. We know that we must be on the y-axis because this is a symmetrical picture. And if you know you have to be on the y-axis, then that tells you that you already know what your x bar is going to be, and that is equal to 0. Now you can find y bar. Please confirm that it is equal to 1.70, which tells you that your centroid is going to be between 1 and 2 in order to keep your semicircle nice and horizontal. For example 4, go ahead and draw example 4. Give this one a good try. Notice for example 5, we have a small difference in this one. We have the centroid being bounded by y equals x and y equals x squared. So when you draw those boundaries, we're no longer going to be on the x-axis. So we have y equals x and y equals x squared, which means that we're going to have some changes for our rectangle. We're going to use a new formula, which is going to be your f of x squared minus your g of x squared, all divided by 2 for your moment about x, and your moment about y is going to be x times f of x minus g of x. So those are some small changes for this problem. Go ahead, try to set this one up, and let's see what you can do. So x bar is going to be your distance, which is x, multiplied by your mass, which we found earlier is just the height times dx, divided by your area of the region. And y bar, once again, is going to be your mass multiplied by your distance from the x-axis, and then we will divide that by the area of the region. Go ahead, calculate those values, and then give page 494 a good try. Have a great day.